Hello, this presentation is for the 2026 CIAP conference, and I thank the organizers for giving me this opportunity. In today's talk, I will talk about some of my work on fair allocation of scarce resources, an important theme in today's world. Fairness is something pervasive that comes up in electrical engineering, in discrete optimization, nowadays in artificial intelligence as well, and I will talk about some of the theoretical works around this subject. I am at the University of Southampton in the UK, in the School of Mathematical Sciences. Let me start off today's talk with this agenda by motivating this subject. Okay, so the motivation that we have out here is that we've got a set of resources that are all substitutable. Substitutable means that these resources could be swapped. One could be swapped by the other, and it doesn't make a difference in terms of the benefit that we achieve. However, not every resource is suitable to all the users that we have. So one resource might be preferred by a particular user. Another user might not prefer a certain resource, so that may not be eligible to be allocated to this user. And our aim up here is not to maximize some utility, but rather we would like to achieve a fair notion of coverage. So we will talk about what fairness means in this context. This setting is quite pervasive, as I mentioned. So in terms of applications, there's applications in healthcare, in public policy, in sustainability, in waste management that abound for such constructs. This work is based on an article that I have published 5 years ago in Optimization Letters, and that would form the main chunk of this presentation. So our goal up here is not to study fair models, not to study the specific models, but rather to study the optimality conditions that will lead us to fairness in different models. Okay, so let's start off with a very basic prototype model. So we have a set of users indexed by I, and the initial coverage of some user I is given by Fi. So that's already data. So that's just handed out to us. After making some allocation via discretionary resources, Xik, we end up having a final coverage of this user I as Yi. So we began from Fi and we end at Yi. The number of resources that we have of different types k is given by B of k. And we have some loss function f that we would like to study. So here is the absolute basic prototype model that you could construct. Okay, so the constraints are quite elementary and they are intentionally chosen to be elementary. So we've got a very limited set of resources. So the first constraint 1b up here says that don't exceed the limit on the resources that you are allocating. 1c is just an auxiliary constraint where we define an auxiliary variable yi, reflecting what is the final coverage of each user. And that final coverage better be less than 1 because we are in the regime of resources are not too many. So we don't want to give any user too many resources beyond his or her need. Okay, and the resources allocated are of course non-negative. So these constraints are quite basic. And with this, we would like to minimize some loss function. So the loss function takes the form of weighted population times some function f. So here is the coefficient of the function f is w times n, where w is some weight assigned to the different user. So as we said, we don't want to just solve this model. for a given f, but we would like to study classes of this function f that would lead us to some notion of fairness. So what does fairness mean in this context? So let's look at different types of fairness which already exist in the literature and those that we have constructed. So let's take this setting that we've got two users, I and I prime, and they both are sharing some resource time. Both of them are eligible for this resource and they both are indeed sharing it as well. So one of them would have a priority over the other. So let's say that's I prime. So if I prime has a priority over I, and in the final allocation, you indeed end up giving I prime a larger coverage. So then that seems fair because this guy had a priority and the final coverage ends up being higher for the same guy as well. So let's call this type of allocation as an appropriate notion. However, if the reverse happens, that you have I prime having the priority over I, but I prime ends up with an allocation with a coverage that's less than I. So then that does not seem fair. So in this setting, what we would do is to construct some notion of fairness which will be sensible for this user I prime. So the setting with appropriate priority is clear. So we don't have to do anything about that. But the inappropriate priority case seems to be something that we have to handle. Okay, so let's look at the case of inappropriate priorities in some more detail. So, and try to define what does fairness mean up here. So we do have an inappropriate priority. So then we would say that some allocation is fair if the following happens. So we've got these two users, I prime and I prime indeed gets I prime indeed has the priority over I, but ends up with an allocation coverage that's less than that of I. So then that situation will be fair if no other resources were handed out to I. So nothing is handed out to I, and the only way that the coverage of I was so high was from the initial coverage F. So you didn't give any new resources to I, but the final coverage still ends up being higher than I prime. So that can only happen if the initial coverage was already so high that despite giving all the resources to I prime, the coverage could not exceed this initial level. So then this notion is still fair because this was just an artifact of the existing status of I being too high. So then this notion will be known as an inappropriate priority. And so this leads to a notion of fairness within the inappropriate priority case. So how could we achieve this inappropriate priority fairness from this from our model? So we proved this via a theorem that if F satisfies certain very basic properties, which are continuity, strict convexity, a decreasing notion, differentiability, then you could guarantee that fairness is indeed achieved in any optimal solution. So there are several functions that satisfy such classes of F, polynomials, logarithmic, exponential, so very generic family. So the proof up here is from the KKD conditions of this model. Okay, so let's look at what happens in the case of appropriate priorities now as well. So the appropriate priority case is already quite fair, but could we construct something stronger up here? So to do that, we define certain other notions. So the first of these is the notion of a balance. So we say that something is balanced if the following equation holds. So that means that the derivative of the loss function is proportional to the weight. Or in other words, this equality will hold for users I and I prime all throughout. So what does this mean? So this means that uh, the partial of the function f is inversely related to the given weights. So if that happens, then you could prove that an inappropriate priority cannot achieve a balance. So the notion of balance may or may not exist in appropriate priorities, but it cannot exist in that of inappropriate priorities. Okay, so then we define a notion of proportional fairness. So this is something that already exists in the literature quite pervasively. So this has been studied in great detail in several other contexts. But what we show is that under these suitable assumptions, such as balance, our class of functions could also lead to the same notions of proportional fairness, such as those that exist in the literature. So what does proportional fairness mean in our specific context? That if you've got these two users, again, I and I prime, and they are sharing a resource, then the resources, the allocation is balanced as well. So if this assumption of balance holds, then this optimal solution would be proportionally fair when you have the final coverages of both the users to be less than 1. So yi and yi prime are both less than 1, and both were handed out some allocation as well. So xi and xi prime are handed out some allocation. So what does this mean? So intuitively, this means that you've got these two users and you do hand up some allocation to both of them, but you don't hand up as much as they would like. So they are both still less than 1. So if that happens, then, and if the solution was balanced as well, so then this notion is known as a proportional fairness. So intuitively, this also means that neither user was denied any allocation from the resource that could be shared, but both were underserved than the capacity that they would like, which is that of matching 1. So the allocation will be then known as proportional fairness. So when is proportional fairness achieved is the next natural question. So once again, you could prove this with quite an elementary class of functions. So the same class of functions as before: continuity, strict convexity, decreasing nature, differentiability, but with the additional assumption of having a balanced solution alongside. Plus the second assumption of having a strict complementary slackness alongside. So if that happens, then you could prove it once again from the KKT conditions that the solution ends up having a proportional fairness. Okay, so far we looked at resources that were scarce, but what does scarce really mean? So to do that, we could compare it with what's the opposite of scarce, which is abundant resources. So let's look at these in some more detail. So abundant resource means that you hand out all the resources. So that's the left-hand side, and all the allocation that you did for resource K could not exhaust the availability of the resource K that you had. So this equation held with a strict inequality. So if the resources are abundant, then intuitively we would expect that everyone who deserves the resource or who even seeks the resource would be allocated something. Or rather their complete share. And indeed, that does happen. That in this situation, so all the users who are eligible to receive resource K do end up having the final coverage of exactly 1. So in the scarce resource setting, the opposite should happen. But what does that really mean? So we could have a nice result up here which says that in this particular setting, if you've got any user who is underserved, so that means there's any I for which the yi is strictly less than 1, then all the resources that this user was eligible for, so that's k of I, the subset k of I, then those better be fully allocated. Because if not, then this resource should have been allocated to the user I to fulfill the quota. And the proof of these results is again from the KKT conditions of this optimization program. So let's try to summarize what have we done so far. So the inappropriate priority case leads to fairness. So that was the case that had to be discussed. Because inappropriateness is not directly fair, but but you do end up showing that this particular class of functions, which is so generic, does end up achieving fairness even in the inappropriate case. The appropriate case is already quite fair, but if you add these two notions of balance as well as a strict complementarity into it, then you could lead to you do end up with something that's proportionally fair as well. So when do you get such a strict complementary slackness? So I don't know the answer, but if you have any ideas, then I will be happy to collaborate on them. Okay, so everything up here was motivated by a previous work that we had done as a large team. So that was during as a retrospective study after the 2009 H1N1 pandemic, where the state of Texas allocated 4 vaccine types or 4 resources, all of which were scarce, to 5 population groups across the 254 counties in Texas. So that were considered a special quadratic class of functions. And a special case of this work ends up having the ends up satisfying this particular function. So this is a polynomial function, and as we said earlier, that polynomial functions do belong to this generic class that we study. So that work showed that fairness is achieved and proportional fairness is achieved as well. So you could look at it with this QR code. So more specifically, so here are the 5 priority groups, and the sixth is the all the priority groups aggregated. So how do they look like? So the 5 priority groups were children under the age of 3 years, adults between the age of 25 and 64, those with high risk, and so there's 5 of these groups that were identified by the health authorities in Texas. So the blue dots denote the coverages for them, the prior coverages. So those are the Fs in our notation. So you see the blues are all over the place. But after handing out the remaining discretionary resources, so the Y, the final coverage, so that ends up practically horizontal. So that's these lines. So that shows that no group was systematically disadvantaged due to scarcity of resources. So that's a good result. And then the mathematics of the extension for such a model, that which we saw today, was done in the follow-up work that I showed you. Okay, so currently we are extending these works. So in two particular goals. So in the first goal, we try to pursue the line of achieving distinct solutions Y for two users. So we would like that the two users I and I prime end up having coverages that are distinct from each other, reflected in terms of their weights. So if the weights are strictly unequal, having an absolute priority, So then what could we do to achieve this? We do have the initial coverages and the population, of course, for them. So then the reachable interval for any user could be between the lower interval, which is that of F, where it starts from, and the upper interval could be either 1. So when this happens, when the user achieves everything that it wanted, or if all the resources were handed out to this particular user itself, and then you end up having the upper bound. So what we would like to avoid is this case of a strict unclear priority where the two users have the same final coverage. So the first two cases are clear in terms of policy making, that one user has either an inappropriate priority or an appropriate priority as reflected by their weights. And so we really want to eliminate the SUP up here. And then we could look at some conditions that would ensure such ties in practice. So for example, if the resources are so abundant, then every user ends up having a final coverage of 1. So then this notion is vacuous. So those are the kind of conditions that we are studying in this work that's currently under review. So our goal up here was to design a model that's minimally invasive from the original model, that still achieves the notion of fairness, but tries to avoid this SUP condition. So how could fairness still be maintained in this new setting? So in the interest of time, I will not go over the second goal, but that's in the slides as well. So let me just wrap up by presenting that these were the two papers that have been published, in addition to the third that's in review. So here's the theoretical work that was largely the crux of this presentation today, published in Optimization Letters. And then the original motivation was published in PLOS One earlier as part of a group where this study really kicked off with the analysis of the model for Texas. So here is my email, and if there are any questions, I will be happy to answer.